Welcome everyone to today's webinar, Mastering Scalable Radar Signal Processing with AMD Versal Devices. We're thrilled to have you here today as we explore advanced techniques and strategies for leveraging the power of Versal in scalable radar signal processing. Whether you're a seasoned engineer or just starting out in the field, today's session is designed to equip you with the knowledge and insights needed to enhance your radar signal processing project's efficiency and effectiveness. We're going to be sharing our first-hand experience working with Versal Devices in order to help you achieve scalable, high-performance solutions. Before we begin, let's go over some quick housekeeping items to ensure a smooth experience throughout today's webinar. Please note that we will have a live Q&A session at the end, so we encourage you to please submit your questions at any time during the webinar using the Q&A button on your control panel. Just feel free to type them in as they arise and we will address them at the conclusion. If you encounter any technical issues or need assistance, just send a message to the chat and our webinar admin team is here and ready to help you. So we're here today to talk about our experience with Versal, and we are proud to announce that we were recently named the Adaptive Computing Partner of the Year by AMD, a testament to our expertise and dedication in the field. In our first decade, fighters did a ton of varied AMD Xilinx work, and so in 2011, Xilinx asked fighters to become their first ever Premier Design Services member in North America. To this date, we've collaborated very closely on opportunities, including on Versal, training together on the latest technology, all with the end goal of helping our clients get their solutions to market as quickly and smoothly as possible. We also boast the largest team of AMD certified engineers and professionals here in North America. So who is Fidus? Well, we were founded in 2001. We have more than 150 people and we're all a North American electronic system design services company. We serve all industries and markets and have 3 brick and mortar locations, 2 in Canada and 1 in the US in Silicon Valley. We've been working with FPGA sockets since 2002, and it would be safe to say that more than 80% of our projects have included FPGA content. We do an incredible amount of work with AMD and collaborate on many different projects. We're proudest of our repeat customer rate. Close to 95% of our customers return year after year with new projects, new business, a real testament to the quality and efficiency of our work in helping improve their time to market. As a full-services electronic systems design firm, our professionals and engineers cover a multitude of service disciplines, including FPGA design, embedded software, hardware, signal and power integrity, ASIC RTL design, and verification. We help our customers by supplying some of these expert skill sets directly, or by managing the complete project from start to finish. So before we jump in, I'd like to introduce our distinguished speakers. First, we have Dimiter Quendry, a senior embedded software designer here at Fidus. He has extensive experience working on Versal devices and has contributed significantly to various projects on this device at Fidus. Next up, we have Jason Timpe, a radar and EW system architect at AMD. He brings a wealth of expertise in radar and electronic systems and will provide us with unique insights into the capabilities of AMD Versal devices. And joining us for the Q&A session will be Bashir Burkhan, a system and algorithm architect here at Fidus. He is a well-published author on topics such as verification, circuit design, and system architecture. So without further ado, I will hand it over to our speakers to kick off today's session.
Today, we're going to be presenting a radar reference design for the VCK190 evaluation board with the AMD VC1902 Versal Core device. This is a joint design developed between Fidus and AMD. In this presentation, we will discuss some of the problems inherent in creating a scalable radar demonstration platform, and then we'll go into our approach for the reference design and how Fidus was able to implement the design quickly. And finally, at the end, I will demonstrate the design. One of the problems we have when we talk about demonstrating signal processing capabilities for radar platforms is that most requirements for the design are really focused on the interaction between the radar and the target, how the radar performs in terms of range, resolution, and the ability to avoid jamming or the ability to filter out clutter. This defines how the radar performs at the system level. On the other hand, when we talk about demonstrating signal processing capabilities, whether in the effectiveness of our algorithms or in the compute power of a device such as the VC1902, our specification is at a lower level. How much bandwidth can we process, the sample rates we can operate at, the bit widths or data types we can support, and latency. So, if we want to show how changes at the algorithm level are beneficial, we need to tie the performance of the signal processing to improvements at the system level. How we can do this is a key to our reference design. Secondly, we want to have a design that can scale. In this particular design, we are targeting the VC1902 ACAP from AMD. This device is a Versal core device with the AI engines on it, so we are going to be focused on using them to improve our signal processing capabilities. But we want this design to be able to scale up and down for other devices in the portfolio. For example, AMD has recently announced the VP2502 and VP2802, which are Versal premium devices that also have the AI engines. Premium devices have higher I/O bandwidth due to their GTs than the core devices, and so from a radar perspective, it allows us to connect to many more antenna elements and pull more data into the device for computation. These premium devices also have a significant amount of DSP58 blocks in the fabric in addition to the AI engines. So there's a lot more signal processing horsepower even compared to the VC1902 and certainly compared to previous generations of Vertex devices. So ideally, we want a reference design that can potentially scale up to take advantage of more powerful devices in the future. And then on the other hand, we have the AI edge devices, which are smaller and have fewer AI engines and are really mid-range devices. So we would also like a reference design to be able to scale down so that we can show the performance that can be achieved even in a swap-constrained platform. Finally, we really want to be able to show a phase development. And for each one of these phases, we want to be able to demonstrate where we are in the development and show that we are meeting our requirements. In the industry today, it is very important to be able to quickly demonstrate new performance capabilities to win that contract, and also to show the customer that you're meeting the milestones and that the design is going to work in the end. Similarly, our approach to the reference design was to do it in phases. Where we are right now in that development is that we're going to demonstrate phase 1 performance. The focus for phase 1 was on a rapid development that would create a quick demonstration platform that would be able to show the capabilities of the hardware and show that our algorithm is going to perform as expected. Also to set up solving the various problems that I outlined in the first 2 sections. In phase 2 of the design, we want to increase the capabilities of the system, extend the algorithm, and build a more fully functional system. And then, as we move on to later phases, we can add more and more capability into our system. But at each step, we want to be able to demonstrate that performance and show to our customer that we're moving in the right direction. The algorithm that we chose to implement is the space-time adaptive processing for radars. If I have a radar on the ground and I'm trying to detect a moving target, then reflections back from the stationary environment is clutter that is going to cloud my perception of the target. But because the clutter is not moving, I can use Doppler analysis to filter out anything that has zero motion. And so it is easy enough to remove that clutter from the scene and focus on moving targets. This becomes more challenging if the radar is instead installed on a moving platform, such as an aircraft, which is looking for moving targets on the ground. Now, because of the motion of the platform itself, the background is no longer stationary, but has a relative motion. So the ground in front of me is going to look like it's moving towards me, and the ground behind me is going to look like it's falling away from me. My clutter return has an angle-dependent Doppler shift. So I want to do my filtering in both space and time. I want to do my beamforming in the spatial dimension, but I also need to account for this Doppler shift, which is also related to the angle. On the left, you can see a return without the stat processing, where the return from the clutter has caused a smearing of the radar pattern. On the right, you see an ideal filter that would null out that clutter to give us a better pattern. Notice that we have also introduced a jammer into the system. This is a barrage jammer, so you can see that it is broadcasting across a range of frequencies, but it is at a fixed location relative to my platform. And so we would also like our STAP algorithm to be able to filter out that jammer if possible. Ideally, our space-time adaptive processing will create this filter and then apply it so that I remove these interfering signals and the clutter and focus in on my target. This processing also has to be adaptive because as my platform moves or as the environment changes, the specific filter that I need will change. So the algorithm has to adapt as time goes on. When we look at how to do space-time adaptive processing, basically we're going to create a radar data cube with the number of antennas in one dimension, which is our spatial dimension. The second dimension is the number of range samples. So from a given antenna, I send out a pulse and I sample the return, and that provides the range to the target. And then I'm going to use a number of coherent pulses to perform my Doppler processing, so this provides the third dimension of my cube. So if we look at the data cube, our stat processing is going to filter in the spatial and Doppler dimensions as shown by the green slice in this diagram. But there are many other types of radar processing that all use different portions of the same data cube. So in general, we can create a radar architecture which gathers the data cube and then selects some subset of that data cube and does processing on it. And then I'm going to use the information from that processing to make some decision about what I do next at the overall system level. That architecture is well suited to several different DSP functions that we can perform on our radar data. So that architecture speaks to the scalability of our design and our ability to do different things. In our reference design, even though we are focused on space-time adaptive processing, we want to structure our design in such a way that it can easily be adapted to other types of processing as well. And again, when we talk about scalability and adding performance, we can think of how a device like the VP2802 would allow us to add additional antenna elements or possibly operate at a higher sample rate. In both cases, this is just growing the size of the cube, and so it is easy to modify our design to handle the larger cube and understand the data and computation requirements needed to do this. So with this architecture, we see that an ACAP is very well suited to this. There are embedded memory controllers, hardened memory controllers that allow us to collect the data cube. We have the ACAP, the AI engines to do the signal processing that we need, and then we have the processing system for the decision making based on our results. Looking in more detail at the space-time adaptive processing and what it's doing, we see that it takes several of the other slices and uses them to calculate the effect of the environment on our radar by calculating the covariance matrix. We can then use this along with our steering vector to create the weights which will undo the effect of the environment and leave only our targets. We apply this filter to the slice of interest to remove the clutter and jammer and reveal the target. I mentioned earlier the phased approach, and so for phase one, we focused on the weight application portion of the algorithm. This is just a matrix multiplication, so we know that the AI engines in the VC1902 are very good at doing this. So it's a good way to see some quick benefits in our design. This serves as a good starting point for trying to leverage the power of the AI engines to do the space-time adaptive processing. So for phase one, we only implemented the weight application, and the data selection and weight computation is done externally in MATLAB. I mentioned at the beginning how we wanted to tie our algorithm performance up to system level performance. In order to do that, we have to be able to model the environment and the rest of the system to test our implementation within the context of the larger environment. A good way to do that is to leverage the STAP example design from MathWorks. We took that design as our starting point because MATLAB has modeled the transceivers, the antennas, the platform, the jammer, and the clutter. This allows us to focus on the signal processing algorithm that we want to implement in the VC1902. At the system level, we can make adjustments to the model to fit the system specifications that we have to meet, and then we can tune the algorithm in MATLAB to make sure that we're meeting our system level performance. Then, when we take the algorithm and we implement it on the AI engines, we've got something to compare against and a way to verify that the implementation in hardware is going to behave correctly at the system level and achieve the desired performance. Likewise, we can iterate this process to make the problem more difficult to gradually improve our system, demonstrating each step along the way how our changes at the hardware or algorithm level are translating to system level improvements. To start with, on the right, you can see the parameters that we are implementing. Initially, we're just building off of the MathWorks STAP example, so it's a pretty small example, but it does give us a quick way to get started as part of our phase one design. With that, I'm going to turn it over to Dimitar to provide some more details on the design and how it works.
Thank you, Jason. The main task implemented during this phase was the application of the STAP weights. This operation requires the multiplication of the conjugated complex weight vector with the STAP cube. Recall that the cube dimensions represent 6 antennas, 10 pulses, and 200 samples. The conjugated weight vector dimensions were reshaped from a 6 by 10 element vector to a 60 by 1 element vector. The STAP cube dimensions were also reshaped to a 200 by 60 matrix for each STAP cube slice. This complex matrix multiplication was partitioned between 10 AI engine kernels running on separate tiles concurrently. The desired output from each kernel is a single vector with dimensions of 200 by 1 elements. The kernel results were then sent to the PS side via GMIO and concatenated in a single vector. This vector was packetized and sent to MATLAB client via TCP/IP. To expedite the development of the submatrix multiplication for the filter application, the Level 2 General Matrix Multiplication AI Engine kernel VITES DSP libraries from version 2021.1 were used. Now, from a software architecture standpoint, there are two main areas regarding design decisions: algorithm partitioning and data movement methodology. Initially, we started with the implementation of a custom kernel that used the AIE intrinsic API. Due to project timing constraint, it was decided to leverage the VITES. Due to project timing constraints, it was decided to leverage the VITES DSP library's general matrix multiplication kernel and adapt that to the application at hand. The current implementation of the general matrix multiplication has constraints on the dimensions of the input matrices A and B. This kernel does not support vector-to-matrix multiplication. To get around this constraint, the weight vector was duplicated to form a 60 by 2 element matrix that conforms with the input matrix kernel requirements. With regards to data movement, there are two interfacing methods to the AI engine kernels: PLIO and GMIO interfaces. When using IP blocks on the PL side that communicate with the kernels using axis streaming interface, the PLIO interface can be used. The other interface is the GMIO interface, which uses memory mapped attributes that make connections from the PS DDR memory to the AI engine data memories directly via the network on chip without going through the PL side. In this case, it was decided that due to the relatively small size of the cube, the GMIO interface was optimal for the scenario under consideration. Let's take a quick look at the host user space software architecture. It leverages the Boost asynchronous input-output libraries to implement a TCP server that communicates with a MATLAB TCP client program running the simulation. The aim of the MATLAB TCP client is to send the weights and stub cube data as well as receive the stub results from the applied weights. To accomplish this, a custom serial framing protocol was implemented to send the stub cube and weights as well as receive the incoming results from the AI kernels. The incoming data is parsed based on framing headers responsible for demarcating the stub cube frames and weights. The outgoing resulting data is also framed and sent via TCP/IP to the MATLAB client for comparison. On startup, the host application takes a command line configuration for TCP/IP port assignment. Once the TCP server running on the Cortex A72 application processor is started, it waits for a connection from the TCP MATLAB client. The cube frames and weights are then received, parsed, and written to the GMIO allocated memory. The next step is starting the graph. Once the stub results are available, the data from the 10 kernels is concatenated, framed with appropriate flags, and sent back to the MATLAB TCP client for comparison with the MATLAB Golden reference design. Now, this solution was implemented as a hardware-in-the-loop application with a Versal VC1902 development board running the weight application based on data received from the live Simulink model running on the MATLAB side. Both stub cube data and weights are single precision complex floating point numbers created on the MATLAB simulation. The data is received via TCP/IP, depacketized, saved in a pre-allocated section in DDR memory. Then both space-time matrix and weights are sent to the 10 AI engine matrix multiplication kernels running concurrently. The AI engine graph is initialized, and once the computation completes, the resulting vectors are then sent back to the PS DDR section via GMIO. The final step is packetizing the results and sending those back to the MATLAB client side for comparison with the Golden ADPCA MATLAB model. Going back to Jason now.
Thank you, Demeter. These pictures show the expected performance of the STAB algorithm. What we see on the left is the return from the 6 antennas on a single pulse before the STAP filter is applied. In our model, the platform is flying at 1,000 meters, and so most of what we see is ground return, and we cannot distinguish the target, which is located at 1732 meters. However, on the right, we see the result of the application of our STAP filter, which is a combined return that should very clearly show the target at 1732 meters. With that, I will run the demonstration. I have a VC1902 evaluation card here with a serial connection to my PC, so we will watch it boot up. The finest design is on the SD card installed on the VC1902, so that is how we're booting the VC1902. Once it boots up, we can configure the Ethernet so that MATLAB will be able to connect to the board. Now we start the host program that runs on the processing system of the VC1902. Once we do this, the host program is waiting for the data cube and weights to be sent from MATLAB. I also have MATLAB running. We have a script in MATLAB that is going to set up the Ethernet connection to the board, and then from there, it will start the Simulink block diagram. It will then run the Simulink design to generate the radar data. The Simulink design is simulating the transmission of the 10 coherent radar pulses, as well as calculating the return reflecting off of the clutter and reflecting off of the target. It will also simulate the interference from the jammer. It will model the behavior of our 6 antennas and create the data cube needed for signal processing. Once the data cube is constructed, MATLAB also calculates the weights through its own STAB algorithm, and then the weights as well as the data cube are sent via Ethernet down to the VCK190 board. Then, as we said, the algorithm running in the AI engines takes those weights that were calculated by MATLAB, takes the data cube, and applies the weights to the data cube, calculating the single return. Once that return is passed back to MATLAB through the Ethernet, MATLAB can now compare that return to the return it calculated using its own STAB algorithm. So we have overall system-level performance that we are modeling in Simulink, and we can show that the algorithm running on the hardware and make sure that it meets all of our requirements. The goal in later phases will be to scale this design up to be able to perform STAB on larger data cubes and also to do the weight calculation in the hardware as well. One of the downsides of our current approach is that the Simulink design does take a while to run. So we're limited in the number of data cubes that we can process because of this. In the future, we will create data cubes in advance and then push that data through the Ethernet quickly rather than running the Simulink design every time. What we see in the results is the raw return here, where you can see the interference from the clutter and the jammer. You can also see over here the weight filter calculated by MATLAB. We can see in the upper left the output of our STAB algorithm. The red is the data that came back from the AI engines, and the blue is the data that was calculated by MATLAB. And when we look at the error, we basically have zero error between these two. So it indicates very clearly that our algorithm, as implemented in the AI engines, is performing correctly. And so, as we modify our system design or modify our algorithm in MATLAB, we can verify that our implementation in hardware continues to track the performance. Even if we don't modify the algorithm in MATLAB, but instead make improvements directly in the implementation, we can still test against various scenarios as modeled by our Simulink design. As we change the behavior of the target, the clutter, or the jammer, maybe add more jammers, to make sure that we are going to meet our system level specifications. That's the end of our presentation for today. I hope that it was informative. As I mentioned, AI engines are a new capability that are part of the AMD Versal series, both in the Core and Edge families, as well as the new Versal Premium devices. And they are very well suited to a number of radar signal processing algorithms, including STAP. If you are interested in learning more about how to get started with AI engines for signal processing, please reach out to your AMD support team with any questions, and we can help you plan out how best to approach your own algorithms and be able to demonstrate them very quickly in the AI engines. Thank you very much, and thank you also to Demeter for helping to present this design.
Excellent. Okay, thank you so much, Demeter and Jason. I would like to now ask and welcome Bashir, Burkan, and Demeter to join us on this for this live Q&A. So while we're waiting, if you have any questions, we've seen a couple come in. If you could please pop them through the Q&A function down the bottom. Okay, excellent. I see Demeter there, and Bashir is there. He is. That's great. Bashir, hello. Nice to have you both here today. So I do have a question first here. So I will let either of you answer it. But it looks like here, so David has asked, what part of the ADPCA pipeline was offloaded to the AI engines on the Versal VCK? So maybe to you, Demeter.
Yep, I can take that one. Hey, everyone. So as mentioned, the implementation of the STAP ADPCA pipeline was completed in a phased approach. So the presentation you just saw established the first phase of the STAP project. During the first phase, the main deliverable was the application of the weight vector to a slice of the STAP cube to obtain the test statistics used to determine the target presence. For phase 2 of the STAP algorithm, the complete STAP algorithm was implemented in the AI engines. Similarly, during phase 3, a polyphase channelizer bank was also implemented, working in conjunction with the wideband STAP application. So the main aim of the STAP algorithm is basically the identification of the target in the presence of clutter and jamming. The detection problem can be framed as a statistical hypothesis where the received data is a function of the overall interference being the sum of the clutter vector, jammer vector, and the background noise, plus the product of the target amplitude with the spatial temporal steering vector. In practice, for the first phase of the project, this meant the calculation, for the second phase, this meant the calculation of the covariance matrix, the weight vector, and the application of the weight vector. For the first phase, it was simply focused on the application of the weight vector W to slices of the STAP cube. And that task required applying the weight vector to a test cell data to obtain the test statistics. And this was implemented using the AI engines on the Versal AI Core Series VC1902 device. Yes, to summarize it succinctly, the weight vector is basically proportional to the product of the inverse estimated interference covariance matrix received from the training data, as well as the product and its product with the steering vector. So this actual weight vector is calculated as the product of the ECI matrix and the steering vector. And the requirement was implementing matrix multiplication, parallel matrix multiplications of this weight vector with slices of the cube, and calculating their result. This result was then sent to the processing subsystem, the Cortex A72 microprocessors, where it was compared with a threshold, and then which was used to declare the target presence when the resulting test statistic exceeded a programmable threshold. The VITIS AI DSP general matrix multiplication library was what was actually used during the first phase. This component was used for complex matrix multiplications using complex floating point data types. And for the first phase specifically, GMIO interfaces were used to share data between the application processor and the AI engine array. For the second phase, we ended up using HLS DMA, so there were a number of IP blocks on the programmable logic section. Hence, the interfaces were revised to use PLIO interfaces for each of the custom kernels. So yeah, the GMIO attribute was what was used for the kernels. That's basically it. Finally, what was done was basically writing the weight vector and the cube slices to the DDR memory, as well as reading the results of the weight application and then sending it to the MATLAB TCP server, as was mentioned, for comparison with the golden model.
Thank you, Dimitar, for that answer. Okay, I have a question here. Bashir, probably best I send this one to you. So what AI engine kernels were created specifically for this work? Or were kernels already made used? If so, can you list them if they're publicly available? And second part is also, do you have enough precision in AI engines to process the samples? CINT16 or floating point usage? That's complicated. I'm handing it over to you, Bashir. Oh, Bashir, we can't hear you.
Sorry.
Oh, there you are. Yep, you're good.
Yeah, I'm good. You can hear me? So I will take the second part, the CINT16 or floating first. So I will jump directly to phase 2. Actually, in phase 2, we implemented, we did the job and we implemented all the part of the step. And more particularly, we implemented actually the part of the ADPCA. It's the low rank because of it's the low complexity. As you know, the baseline for the step algorithm is the SMI, sample metric conversion, which is based on the inversion of the covariance metric of the whole cube. So for the ADPCA, it's way simpler. We are just calculating the covariance metrics between two pulses, adjacent pulses. So for the operations, actually, the type is everything is done in the AI engine in float, so in C float. So all the operations are actually done in C float. The MATLAB, when we generated synthetic data, we generated in CINT16. However, we did the conversion just before doing the operations. As which parts of the kernel we implemented for the phase 2, it's actually more complete. Actually, we implemented all the operations of the step algorithm, which include the calculation of those covariance matrices between two pulses, then the inversion of those matrices, and some other operation to create an effective covariance metric, and finally a multiplication by a space-time steering vector to create the weight. At the end, it's weight application, which is exactly equivalent to what we did in phase 1. So all those actually, all those kernels actually were implemented from scratch by the team, and one of the implementer is Dimitar. So he can actually, if he can elaborate a little bit more about some of the kernel that you implemented.
Yep, thank you, Bashir. So as Bashir mentioned, the complete step pipeline was mapped on the AI engines, and what was initially implemented during the first phase, the weight application kernel that leveraged the various libraries, it was completely refactored and replaced with custom kernels. A number of kernels were implemented from scratch using the high-level C++ library, which included, number 1 was the covariance matrix kernel. Number 2 was the vector addition kernel. Number 3 was the covariance matrix accumulator kernel. All the first 3 kernels were basically the building block components for building the covariance matrix. Then there was the steering vector kernel, the matrix inverse kernel, which was implemented initially with the Gram-Schmidt-Schwarz-Ruti-Schauser method, and then for the deliverables, it was implemented using the householder method. Finally, there was the matrix row adder, as well as the effective covariance inverse matrix. And yeah, finally, it was the weight calculation number 1, and then the weight application number 2. Now, bear in mind that during phase 2, there was a major refactoring of the complete implementation. So what was initially implemented using GMIO interfaces for sharing data between the application processor and the AI engines was implemented using HLS read and write DMAs. So the interfaces were converted from GMIO buffers to PLIO buffers. Yeah, that will summarize all of the kernels that were implemented on the engine, at least during the second phase. For the third phase, we ended up implementing a polyphase chain laser bank, but that was in addition to what was already implemented.
Yeah, and that's just to complement that the latest phase 3. What Dimitri mentioned about the polyphase is just to emulate a wideband radar. Up to now, we're just tackling narrowband radar.
Got it. Okay, I think we have time for probably 2 more questions. So this is question number 1. How do AI engines stack up compared to the DSP58 blocks on Versal for this application?
Yeah, good question. So this is kind of an open-ended question in the sense that there are a couple of assumptions that have to be made over here, because what we ended up actually doing was implementing the complete stub pipeline on the AI engines. So the main assumption is that the compiler would map all the mathematical operation, arithmetic operation to DSP58 slices instead of using lookup tables. So the VCK190 development board we used, it contains the VCK1902 chipset, which is part of the Versal AI core series. This device contains 400 AI engines, which are organized as a 2-dimensional array. In addition to that, on the programmable logic side, it also contains 1968 DSP58 engines, as well as dual Cortex A72 microprocessors and Cortex R5F real-time cores. The latter were not used, at least during the first phase. So what was done initially for each kernel that I mentioned before, for the covariance matrix kernel, the vector add kernel, the covariance matrix accumulator, the steering vector kernel, the matrix inverse, the row adder, the effective covariance inverse kernel, the weight calculation, and the weight application. For each of these kernels, one by one, we ended up building a table in order to arrive at an estimate of the number of additions, subtractions, multiplications, divisions, inverse operations, as well as the square root operations, which were needed for on the householder matrix inversion implementation. So all of these were tabulated, and they provided a ballpark estimate of around 460 DSP58 slices, which amounts around 23%. Bear in mind that this, again, is just an estimate, because number 1, the implementation on the PL was not done. And then number 2, the assumption is that from a resource perspective, if you were to implement this on the PL, design the control path and the data path for each of those kernels, there would be additional resource consumption, both on the memory side for Ultra RAM and BRAM. Whereas that's item number 1. And then item number 2 that we have to keep in mind is that when implementing these algorithms on the AI engines, there is some attrition, meaning 1 or 2 engines can be used only for the memory buffers. On the AI engine side, from the implementation, the actual application uses around only the stub node, the polyphase chain laser filter bank, uses around 86 AI engines out of 400. But the main advantage over here is that the AI engines can be run at 1.25 gigahertz. You don't have, from the developer perspective, you do not have to be concerned with timing closure issues, additional effort that would be spent on implementation on the HDL side. That should sum up most of yeah.
Thanks, Demeter. Okay, Bashir, I have one for you. Can you walk us through the implementation data path from high level of abstraction?
Yes, this is actually with respect to phase 2, it's more interesting actually. So in phase 2, actually, as I said before, we implemented the full stack at the IDPCA, the lower rank 1, and the implementation is a pipelined one. So we didn't use data converters. So to emulate the interface, actually, we transported the cubes into the DDR, and from the DDR, we used the data movers to push data into the AI engine. So with the first step of the design, I believe Demeter mentioned already that is the training cells selections. As you know, that the covariance matrix is only calculated on selected cells, and we used about half of the cube as a training cells, and the cube size is 4,000 cells, 4,000 samples times 4 antennas, and we use also 10 pulses to build that cube that we are going to push into the AE. As I said, first step is just to push 2,000. And as they arrive, as we push them from the DDR, so the training logic will drop the cells that are not needed to calculate those covariance matrices. The first step actually, and at the same time, we are pushing it from one of the DDR. We are using VC1902, and VC1902 has actually 2 sets of DDR, DDR4 and LPDDR. We are using DDR4 to store data cubes that we are going to push to the AE that mimic the interface coming from the interface, and we're using the other DDR with higher bandwidth for storage of the storage of the cube while we are doing the initial calculations of the weights. So it's a pipelined design, and it has 2 steps. The first CPI period is the period that we receive the whole cube. We are using that period to calculate the weights, and at the same time we are on the fly, and at the same time we are pushing it to the DDR, LPDDR. Then once we are done on that first phase, first CPI, 320 microsecond, we move to the second steps, the second pipeline stage, where we apply the weights, and of course we get the filtered return. But at the same time, those 2 stages are working in parallel. At the same time, we are calculating the next set of weight for the next cube. So this is mainly describing from high level of abstraction how the step elements are implemented on the AI engine. Thank you.
Thank you, Bashir. Okay, there's one last question. I think that we might need to wrap it up after this, but the last question is with regard to STAP. Did you implement a full rank or reduced rank method?
Yeah, we said we implemented the ADPCA, which is a reduced rank method. So it's with low complexity, low precision, but low complexity.
Excellent. Okay. Well, on that note, we've now hit 12:15. Thank you both to the 2 of you and to Jason for today's presentation. This presentation recording will be sent by email to everybody that registered for the event. And we encourage you to come and check out our website at fidus.com. And you are welcome to book a consult to discuss your upcoming project, or if you have any questions or concerns regarding the AMD Versal series, we'd love to chat with you and share our experience and best practices with you as well.